In this video lecture, we will discuss about most basic combinational logic circuits of digital electronics. As we know that the addition is the most fundamental operation in digital electronics. So the simple addition consists of four possible elementary operations. The first one is 0 plus 0. Next is 0 plus 1. Then 1 plus 0. And finally 1 plus 1. And these are all binary numbers. So 0 plus 0 is always equal to 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 1, 0. So this is my LSB, the least significant bit, and this is my NSB, the most significant bit. The higher significant bit is always called as carry. So this is the basic fundamental of addition operations in digital electronics. So basically adders are divided into two types. The first one is half adder. And the second one is full adder. So what is a half adder? So remember, a conventional logic circuit that performs addition of two binary bits. Then it is called half adder. And the one which performs addition of 3 bits is called full adder. Addition of 3 bits is called full adder. We can say that a half adder is the addition of 2 bits along with a carry having 0 value. And a full adder is the addition of 2 bits along with a carry having the value 0 and 1. So we need to understand few things about every conventional logic circuits. It may be adder, it may be multiplexer, it may be code converter or anything. So the first thing is block level design. Second one is truth table. Third one is Boolean equation. Which can also be called as Boolean function. Fourth one is circuit level design. So we need to have the idea of all these four things. So let us start with the half adder. So as we discussed that half adder is a combinational logic circuit which adds 2 binary bits. So let us first draw the block level design. So in block level design we will draw a box, and as we know that it accepts 2 binary bits, let the first bit is A0 and the second bit is B0. So in short we will write over here half adder. Now every addition produces two things, sum and carry, and we will name it as S0 and C0. So this is the block level design of half adder. Now let us draw the truth table. So basically as we have two bits A0 and B0 which are my inputs, and we have two outputs, that is S0 and C0. So this is my sum and this is my carry. So with two inputs the possible number of combinations are 4 because 2 to the power 2 is 4. That are 0, 0, 0, 1, 1, 0 and 1, 1. So we know that 0 plus 0 is always equal to 0. sum is 0 and we don't need any carry, so carry is also 0. 0 plus 1 sum is 1, carry is definitely 0. 1 plus 0 sum is 1, carry is 0. 1 plus 1 the sum will be 0 and carry will be 1. As we discussed here, the sum is 0 and carry is 1. The most significant bit is my carry. So this is my truth table. Next we will write down the Boolean equation. So we will first write down the mean term representation of sum and carry. So let us write down the mean term equation for sum. So we can see the sum is equal to high in these places, this one and this one. So the decimal value of my binary inputs are 0, 1, 2 and 3. So we can write down the sum equation, that is S0 with input variables A0 and B0 is equal to summation mean term 1, 2. So we can write here 1, 2. So this is the mean term representation of my sum. Now similarly we can write down the mean term representation for carry, that is C0. The input variables are A0 and B0 will be equal to summation mean term. Let us see, the C0, the C0 or the carry is high at this place only. That means the decimal 3. So this is the mean term representation of sum and carry. Now let us write down the equation with the help of K-map. So we will draw two K-map, one for sum and another for carry. So this is my sum, that is S0. This is my carry, that is C0. Let my variable A0 is here, A0 complement A0, and here we can write B0 complement B0. This is A0 complement A0. This one is B0 complement B0. We can write here 0, 1, 2, 3, 0, 1, 2, 3. So sum is equal to 1 in the cells 1 and 2. So let us fill the cells of K-map. Here we will write 1 and here we will write 1. So we can see that the ones are present in the diagonal positions. So the grouping is not possible. So we can write S0 is equal to A0 complement B0 plus, and this one is A0 B0 complement, which can finally be written as S0 is equal to A0 XOR B0. So this is the Boolean equation for sum. So let us find out the Boolean equation for carry. So C0 is equal to mean term 3. So we have to put 1 over here, and the value of this carry will be C0 with variable A0, B0 is equal to A0 B0. So this is the Boolean equation for carry. Now with the help of Boolean equation we can draw the circuit level design. So let us draw the circuit level design. With the help of this Boolean equation. So as we have two number of inputs, I'll drop two vertical lines. The first one is A0 and the second one is B0. Now S0, which is my sum, is the XOR connection of the two inputs A0 and B0. So we can draw an XOR gate with the help of inputs A0 and B0. So this is my S0 sum. Similarly, my carry is C0, which is the AND connection of the two inputs A0 and B0. So let us draw an AND gate by the help of two inputs A0 and B0. So this is my carry, that is C0. So this is the final design of half adder. So in this way we can design the half adder by the help of two binary inputs A0 and B0. In the next lecture we will see how to design the full adder. Thank you.